We're going to start off the year with a review of functions. The domain of a relation or function is the set of all x values in the relation or function. It could also be thought of as the set of all the independent values. Whereas the range is the set of all y values in the relation function, or the set of all dependent values. For example, if we have this graph, which is the graph of the function y equals x squared minus 2x minus 3, let's determine its domain. The domain looks at all the x values. So we need to determine the smallest x value and the largest x value. So these arrows indicate that the function, the graph, continues to go up and to the left and up and to the right. So the smallest x value, or the one that's most on the left, is negative infinity, whereas the largest one is going to be positive infinity because it keeps going to the right as well. In other words, we could say that the domain is any real number, or x can be any real number. For the range, we need to look at the y values. Here it's easy to see that the smallest y value is here at y equals negative 4. And then remember, the arrows mean that this function is going to keep going up to positive infinity. So we go from negative 4 up to positive infinity, or we can say that y is greater than or equal to negative 4. There are four main ways to represent relations or functions. And this is from your textbook. This shows that we can represent relations and functions as a set of ordered pairs using a mapping diagram or using tables and graphs. And this year in class, we'll mostly use the tables and graphs. A function is a relation where each element of the domain is associated with exactly one element of the range. In a function, no x value is repeated. For example, and here we see a relation as a set of ordered pairs. We have the relation with the ordered pairs 1, 3, 2, 3, 3, 3. So if we look at the x values, we have 1, 2, and 3. None of them are repeated, so this is a function. Let's look at another relation. Here we have one with the ordered pairs 1, 1, 2, 2, 3, 1, 1, 4. So for our x values, we have 1 that's associated with 1 as a y, and here's another one. So the x is repeated, and here y is 4. Since x is repeated, this is not a function. No, it doesn't matter that y values are repeated, like in the first example. All the y values could be the same. The relation could still be a function as well, as long as the x values don't repeat. Okay, another statement that I just wanted to remind you about is that all functions are relations, but only some relations are functions. On a graph, you can use a vertical line test to determine if a relation is a function. So the vertical line test is defined as, or is used in that a graph depicts a function if any vertical line drawn on the graph doesn't intersect the graph more than once, or in at most one spot. So let's look at some examples of this. Here we have a graph of a parabola. If I draw a vertical line, I intersect this graph in only one place. Therefore, this is a function. Here's a second graph. This one is sort of S-shaped. And depending upon where I draw my vertical line, I may intersect this graph in a different number of points. So for example, out here, I only intersect it once. But here I can intersect the graph in 1, 2, 3 places. So this graph does not represent a function. It's just a relation. I also want to remind you of function notation. So here we have the equation y equals 3x minus 5. We could also write this as f of x equals 3x minus 5. And that's the way you say this, f of x. It is not f times x. We could also, you might see written y equals f of x, and this represents that y is a function of x. Y and f of x will also be interchangeable in our equations. You may see this form of a function definition. F colon x maps onto 3x minus 5. And this is saying f is a function that maps x to 3x minus 5. An ordered pair, xy, can also be written with function notation as x comma f of x, because remember, y and f of x are synonymous. These f's could be any letter. So f is representing the name of the function. We could have g of x, h of x, p of x, w of x, could have smiley face of x. You'll often see f of x because f is for function, but it doesn't have to be an f. If f of x equals 3x minus 5, then let's find f of 6. Now this is function notation for finding out the value of the function when x equals 6. So let's replace the x in 3x minus 5 with 6. And we get 3 times 6 minus 5. 3 times 6 is 18, minus 5 is 13. So f of 6 equals 13. Let's look at a few more examples of this, also called evaluating a function. So for example, f of x equals x squared minus 3x plus 4. Let's find f of 0, f of 1, and f of 10. F of 0 equals, okay, now remember we're going to replace all of the x's with the number in parentheses, which in this case is 0. So we have 0 squared minus 3 times 0 plus 4, which equals 4. Because 0 squared is 0, minus 3 times 0 is 0, plus 4 is 4. F of 1 equals 1 squared, minus 3 times 1, plus 4. 1 squared is 1, minus 3 times 1, which is 3, so 1 minus 3 is negative 2. Negative 2 plus 4 is 2. So f of 1 equals 2. Finally, f of 10 equals 10 squared minus 3 times 10 plus 4. 10 squared is 100. 3 times 10 is 30, so we've got 100 minus 30 is 70. 70 plus 4 is 74. So f of 10 is 74. Okay, so remember this first one is evaluate f of x when x is 0. The second one would be evaluate the function f of x when x is 1. We could also say for the last one, f of 10 represents what the function equals when x is 10. So these are all different ways of using function notation.